Okay, we are going through the topic of specialized counting studies in which we try to find out the demand of an area. And in this regard, we have already discussed the origin destination studies. And we're going through the cordon counts, which are done within a boundary around an area. And we discussed the different guidelines regarding the setting up of the boundary, the cordon. Okay, and now we will look at one example in which a cordon count has been done. So you can see that starts between 4 and 5 a.m. and they have taken an initial count of how many vehicles are accumulated inside the area. These are the vehicles which are basically parked on the street side, so maybe some of them are on the streets moving. But the reason for doing this count so early is that we don't have any vehicles entering and leaving, so we know this count is stable. And then in the next hour, we count vehicles entering 100, vehicles leaving 20. So entering plus accumulated total 350, and then minus the ones which are leaving minus 20. So the new accumulation is 330. So next time it will be 330 plus entering minus leaving, you get 440. So for every hour, you can find out the accumulation of the vehicles in this manner. Okay, and you can see the maximum is over here in these 2 hours between 10 and 12. Okay, and this is the benefit of this study, that you can find out when is the peak hour and how many vehicles are expected inside the area. And the reason for knowing this, or to know this, is that we can plan for this area in a central manner, in a more comprehensive manner. So about the parking spaces, the street size, and so on. So we treat the whole area as one. Okay, similar to the commercial areas we have, like Souk Manama and Muharrak. So usually people just park at one place and then they walk around the area, because the area is very small and congested and so on and so forth. So the accumulation studies help us to plan for these types of areas where we can provide combined parking spaces and so on, and people can walk around in the area. This is accumulation count plotted, so you can see the time and the count. And one more thing which you can see is the different types of vehicles. So in some cases, maybe you are more interested in the accumulation of specific type of vehicles, for example, trucks in industrial areas. So the accumulation count can be divided into different types of vehicles as well. This is the accumulation count study which we did in Bahrain in 2018. It was done for the diplomatic area, and you can see the results over here. The problem with this study is that you see the accumulation count is still going up while the study finished. This shouldn't have happened. They should have continued till the graph comes back to the normal position. This is what happened here. See, it started at 250 and reached almost the same value in the end. Okay, so the whole accumulation went out of the area. You are back to the initial position. So this is what should have happened in this study as well. Anyways, this is a crossing representation of the accumulation count. So the dotted line is the boundary. These lines are the roads which are coming in and out of the area, roads and streets. Okay, and you can see the directions as well. So this is a two-way road, so you see entering and leaving both. This is a one-way road, so you only see entering and so on. So in this diagram, you can see the location of the crossing. So this is an added advantage of having a crossing diagram. And in the end, you can see the totals over here. It was a 24-hour study, so they added the total vehicles entering and leaving. Okay, and so it gives you the location of the crossings, but obviously then it doesn't show you the time. So every representation has its own advantage. The next type of specialized counting study is the screenline count. Screenline means you divide an area into two zones. Okay, so their division line is called the screen line. Okay, so screen line is the separation between the two zones or two areas. And a screen line count is just like origin destination count with two areas. We already discussed origin destination studies where the number of areas could be any 4, 5, 10, 100. But in Screenline count, it's only 2. But the procedure will remain the same. Everything we discussed for the origin destination counts or Cordon count, origin destination counts applies to this one as well. But obviously the scale is much smaller, so only 2 areas. And when you are making the screen line, again we need to keep the guidelines which we discussed for Cordon count as well. And the most important one was that if between the two zones, if you have an object that is acting as a separation between the two areas, you make this, or this becomes your screen line. Okay, so between the two areas you have a bridge or a railway line or a river or a mountain range. These objects will become your screen line. Okay, so in the screen line count, we are interested in how many people are crossing the screen line, going from one area, one zone to the other zone. So in this figure, you see 2 areas, and between the 2 areas, this is a river. So they made the river as a screen line, although it's not a straight line. And the reason is that crossing the river will be at fewer points as compared to crossing from other highways or streets. Okay, so you make the river as a screen line, so the crossing points are minimized, and this is why we want to make an object, a real object, as part of the boundary of the screen line. If you look at this graph, you will find 3 curves here. One is gross crossing, which means total crossing between the 2 areas or across the screen line. Then we have internal crossing. Internal crossing is the origin is one area and the destination is the other area. Okay, one of the 2 areas is the origin, the other area is a destination. So these are called as internal crossings, and you can see most of the gross part is internal. Gross means total, total is internal plus external, so most of it is internal. Okay, and then we have few external crossings as well, which are very low compared to internal, and these external crossings are those people who are coming from some other area outside this region. Okay, so maybe they are coming from somewhere here or somewhere here, but they are outside the 2 zones in which I have put the screen line, between which I have put the screen line. So this you can see is very low, and this is how it should be. The internal should be very high. If not, if it can be equal to total, is excellent, but it should be very high, and the external should be very low. Okay, because you are interested in these 2 areas, so the most of the crossing should be between these 2 areas. If in your study you find more external crossings, that means your selection of the study is not good, your design of the study is not good. You may have, or you should have, focused on the areas from where the external crossings are coming, instead of focusing on these areas where nobody is coming or going. Okay, so but in this case, this is normal. Internal crossing is very high. That means most of the people are from these areas which are moving in this region. They are from these 2 areas, so this is a good sign. Okay, then this is an example, a real example. We have the King Fahd Causeway. Okay, so it's a bridge between Bahrain and Saudi. So this bridge becomes a crossing point, and the screen line becomes the sea. Okay, so this is a real-time example. Okay, now we will move to the next topic, which is highway capacity and level of surface analysis, taken from the chapter 7 and 28 of the textbook. So this chapter deals with the analysis of uninterrupted flow facilities. So these are the facilities which don't have intersections, but there are some facilities we can count them as uninterrupted, but they have intersections, and this is possible if the intersections are very far from each other. How much far? More than 2 miles. So if you have a highway which has intersection spacing more than 2 miles, that highway can be considered as an uninterrupted flow facility. Okay, and obviously the highways which don't have intersections are already considered as uninterrupted. So we are going to discuss 3 types of uninterrupted flow facilities: freeways, multi-lane highways, and rural 2-lane highways. Freeways are pure uninterrupted flow facilities. That means they don't have intersections. Multi-lane highways and rural 2-lane highways, they fall under this category, where the intersection spacing is more than 2 miles. And the difference between these two is the number of lanes. This one has 2 lanes, the multi-lane has more lanes than 2. So, and keep one thing in mind, the number of lanes are mentioned for both directions. So it's a total. Okay, total of both directions. So 2 lane means 1 lane in each direction. Okay, the procedure which we are going to follow comes from Highway Capacity Manual. It is considered a US standard but adopted all around the world now, and it is published by Transportation Research Board, which works under National Academy of Engineering in US. And the first of this manual was published in 1950, the last one in 2022, and it seems that they will publish another one in 2028. Okay, in 1994, they looked at the calculations of the manual and they thought that this is becoming too complicated for handling, through calculators or Excel sheets. We better design a software. So they came up with a software to do the calculations of the manual. The software was called Highway Capacity Software, but it was specific to the calculations of the manual. And then later on, with the popularity of the manual, when the procedures were adopted by other countries, so other software companies, they adopted their calculations. So they inserted the level of service and calculations and procedures from the Highway Capacity Manual into their softwares. For example, Vism, which is a German software, it has the level of service calculations and capacity and everything which is coming from Highway Capacity Manual. And there are other softwares listed here. So any software which you are using for traffic analysis or traffic simulation, it basically has the calculations from the manual. So according to the manual, capacity is defined as a flow rate, okay, maximum flow rate, not volume. If you go back to the chapter number 1, you will find that flow rate, maximum flow rate is much safer to design for, or much safer to be taken as capacity, because when you take the maximum flow rate, then you are sure that your the capacity of the highway will not fail even in the 15 minutes within the peak hour. If you just take the volume, then there is high chance that you may exceed the capacity in any 10-15 minute period, and it will ruin the entire hour or maybe more than 1 hour. Okay, so capacity is taken as maximum flow rate. The manual deals with highways, so the capacity is in vehicles per hour for those highways, and it also deals with public transport facilities like bus services and train services. So in those cases, the capacity will be persons per hour. And capacity is a reasonable expectation. So according to the design of the highway, we expect the maximum flow rate to be this much. The actual can be a little bit high or low. So this is the error. You need to expect it. Okay, and capacity is by default for a point. But if the characteristics of the point extend to the entire section, then the capacity will not change in the entire section. For example, you have the same number of lanes, the gradient, the curvature, everything is the same for all the points in a 10-mile section, so that whole section has the same capacity. Okay, but by default, it is defined for a point. Capacity can change according to road conditions. We have already mentioned lanes, width, shoulders. It can change according to environmental conditions, heavy rain, snow, fog. Okay, so capacity in these conditions is entirely different from a normal weather condition. Then traffic conditions. Okay, traffic conditions mainly include the mix or the proportion of different types of vehicles. So if you have more percentage of trucks, capacity will be different as compared to when you have less percentage of trucks, because trucks are slower. Okay, and then you have the effect of motorcycles and other types of vehicles as well. And then we have the control conditions. So control conditions mean anything which you are doing on the road to control or manage traffic. So for example, lane markings, speed humps, speed cameras, roundabouts, signals. So obviously, if I remove signal from an intersection and build a bridge, so I played with what? I played with the control condition. So now the capacity obviously will change. Okay, these are the capacities under ideal conditions for the 3 types of highways. You can see for multi-lane highways and freeways, the capacity depends upon the free flow speed. Why free flow speed? Because free flow speed is an indicator of road design. Drivers choose the speed when there is no traffic according to road conditions, and this is what is free flow speed. So free flow speed is an indicator of road design. High free flow speed means better design, and you can see it means more capacity as well. Now you can see here for freeways, the lower speed is written as non-applicable. For multi-lane highways, the high speed is written as non-applicable. Why is that? It is for the reason I already mentioned. Freeways don't have intersections, so they are pure uninterrupted. So designing them for a very low speed, less than 50, is not suitable. Uh, is not sensible. Okay, why do you design a highway that does not have an intersection? Then you design it for a low speed. Same thing for the multi-lane highways as well. They have intersections, so you cannot design them for high speed. They have intersections are far, but you cannot design them for high speed. Okay, one more thing, one more point, that why we are saying that intersections are far, we can consider the highway as uninterrupted, because when they are far, then their effect on traffic is less. Okay, it's not like you pass one intersection and now you are already thinking about the other intersection, that I should slow down, or there are cars in front of you, or you are looking at the signal timing. The intersection is very far from each other, so you are driving irrespective of the intersection. So that's why we can consider it uninterrupted. Okay, for two-lane highways, you can see the capacity is a constant 3,200 passenger cars. Okay, so all capacities are passenger cars, and they are per lane as well. Capacities are by default per lane. Okay, but for two-lane highways, the number of lanes are fixed, so we can give a total number 3,200 for both directions. For one direction, it can be 1,700. Okay, so why not 1,700 for both directions, total 3,400? The reason is, on two-lane highways, these two directions are very close to each other, and in many cases, without any separation or median, people from one direction may go in the other direction to overtake someone. So one direction has an effect on the other. So this effect restricts the other direction. So both of them cannot achieve the same value. When one reaches 1,700, the other one cannot reach the same value because of the effect of the other direction, which has already reached 1,700. So that's why we have a deficiency here in the total. Okay, then the level of service concept was given by Highway Capacity Manual in 1965, in the 1965 edition of the Highway Capacity Manual. This is their own baby. Nobody came up with this concept before. Okay, so why do we need this concept? Because we know traffic, what is level of service? A crude definition is that it tells you about the quality of traffic, condition of traffic on the highway. So we know the highway can be under free flow condition, it can be under capacity condition. Okay, but when you are designing, you obviously you will not expect that the highway will have free flow conditions in the peak hour, because it's high volume time, and you will not want the highway to have capacity conditions in the peak hour, because then there is no factor of safety. You want the capacity to be higher than the flow in the peak hour. So that means now we need intermediate levels between them for our design purpose, because we cannot design for freeway, we can't design for capacity. So the demand in the peak hour should be somewhere between them. So level of service are basically different conditions of traffic, okay, which you define in terms of letters. Okay, so we have a letter for free flow condition, or level of service for free flow condition. Same thing, we have a letter or level of service for capacity condition, but we also have three levels between them as well, three levels of service between free flow and capacity as well. Then we have a condition more than capacity as well, because demand can go more than capacity. So we have a level of service for more than capacity as well. So after knowing why do we need the level of service concept, let us look at the definition. So like I already mentioned, this level of service indicates the operating conditions of traffic under given volume. So when the volume is this much, in what traffic conditions you expect the highway to be, how the traffic is moving under this much volume. Okay, so what is included in level of service? We have, for example, speed and travel time. So when a speed is higher, that means the level of service is good, traffic condition is good. So it's more towards A. Okay, and by the way, the level of service goes from A to F. Okay, A is free flow, F is when demand exceeds capacity. Okay, and so I was telling you that level of service includes speed, it includes travel time. So travel time has an inverse relationship, right? Travel time decreases, level of service becomes good towards A. freedom to maneuver, how easily I can move between the lanes and in different directions and so on. So when this freedom increases, then level of service is good. Traffic interruptions cause you to stop. So less stoppage is good. So less interruptions are good. These interruptions can be because of traffic jams. They can be because of construction activities. They can be because of signals and so many other things. So less interruptions means level of service is good towards A. And comfort and convenience, how comfortable and convenient you feel while you are driving. Okay. So all these things are part of level of service. Instead of having a number for each one of them, so you have 6-7 different numbers, and some of them are not even quantifiable. Okay, so we have one level of service which tells you that the overall condition of the traffic is this. Okay, so as I mentioned, levels of service go from A to F. Here you see the description, a small description. I will give you a more detailed explanation later on for the levels of service which go from A to E. So A is free flow, okay, high operating quality. B is considered practical capacity for rural freeways or rural facilities. C is considered practical capacity for urban facilities. D is maximum sustainable flow, and E is capacity. So we know A, which is free flow. We know E, which is capacity. D is just under capacity. Okay, so the flow is continuing. Okay, so that's why I call it sustainable, meaning the flow continues without any stoppages. What happens in capacity? The flow theoretically should continue without any stoppage, but because of driver behavior, because of small maneuvers within the traffic, for example, changing the lane. So if the highway is at capacity, if everybody is just moving in his or her lane, then there should not be any stoppage. Okay, nobody is looking at the phone, everybody is looking at the road, and so on and so forth. So there should not be any stoppage. But this is not how it actually happens. So in capacity conditions, okay, practically you have stoppages. Theoretically you shouldn't have, but practically you have stoppages. So practically when you have a real sustainable flow, maximum real sustainable flow is level of service D. So you have some spaces available for the cars to use for lane changes or to slow down a little bit and check maps on the phone and so on and so forth. So this is available in level of service D, not any. So that's why D is called as maximum sustainable flow. Now B and C, we called it practical capacity. Practical capacity means what? Up to a certain extent, when the flow increases, the speed doesn't drop on the uninterrupted flow facilities. Drivers feel that even with low spacing, the spacing is getting lower, flow is increasing, but drivers still feel safe and they try to maintain their speed. Okay, but then a point comes where the drivers no longer feel safe. The spacing is so less that they now feel forced to reduce their speed. That point is called as practical capacity. Okay, so in rural facilities, this point comes earlier, like at a low level of flow, and for urban facilities, it comes much later. Okay, so we call it practical capacity for urban facilities. So that happens in level of service C. Okay, now level of service itself is a letter, but how do we get to that letter? We need a number behind it. So that number is called as a service measure. So service measure is the value which will give you the level of service. Okay, the value which will give you the level of service. Okay, and this varies for different types of facilities. So if you have uninterrupted flow facilities, which we are discussing right now, 2-lane highways, multi-lane highways, freeways, segments, and so on. For most of them, density. You need the density to find out the level of service. For 2-lane highways, we need percentage time spent following and average traveled speed. Okay, so we don't need the density for 2-lane highways. What do we mean by it? We will discuss it later on when we come to the topic of 2-lane highways. For interrupted flow facilities, we are mainly dealing with delay, except for urban streets where we are using average traveled speed. Okay, but for most of the interrupted flow facilities, meaning different types of intersections, delay gives us the level of service. For other road users, for example, transit service, public transport service, pedestrian facilities, bicycle facilities, our the main criteria is the user perception. So we ask the people, okay, rate the facility on this scale from 1 to 5 or something like this. So these are the service measures, the values which will give us the level of service. Okay, then there we now coming back to the uninterrupted flow facilities. Every level of service has a flow rate value, maximum flow rate value, that is known as service flow rate. For every level of service, there is a maximum flow rate, and that maximum flow rate is called service flow rate. Okay, so when you exceed that maximum value, your level of service changes. So level of service A has a maximum flow rate, for example 1000. So when the flow rate on the highway exceeds 1000 passenger cars, the level of service is no longer A. Okay, you can call it the capacity of that level of service as well. If you have the flow rate, multiplying it with peak hour factor converts into volume. So if you have the values of service flow rate, you can multiply them with peak hour factor, it becomes service volume. Okay, so like I said, every flow rate, every level of service has a maximum flow rate. The maximum flow rate for E is called capacity. That's why we said level of service E represents capacity conditions. Okay, so the maximum flow rate, the service flow rate for E is called capacity. And after that we have the Q formation. Okay, in these slides we will discuss basic freeways and multi-lane highways. Okay, because they are considered to be the same according to the procedure in the highway capacity manual. So the part of the freeway which we will discuss is called basic freeways. Basic freeways is the part of the freeway which we are going to discuss in these in this course. So what are basic freeways? These are pure uninterrupted flow facilities, no intersections. Okay, the in and out on the highway only happens from the ramps. Okay, then they have, so these highways have full control of access. Okay, the only change in the design of these highways according to the number of lanes. Okay, so number of lanes must be given for basic freeways. Then we have multi-lane highways. Multi-lane highways are uninterrupted flow facilities because of their intersection spacing, because the intersection spacing is more than 2 miles. So they're not pure uninterrupted, but practical they can be called as uninterrupted. So multi-lane highways, they have more than 2 lanes. That's why I call them multi-lane, and they may or may not have a median. If they have a median, we call them divided. If they don't have a median, we call them undivided. Median is the object which you have between, or the separation between you have between the two directions of the highway. So in case of freeways, clarification, in case of freeways, there's always a median. So you cannot have undivided freeway. So we don't bother. If it's a freeway, it has a median. And similarly, we don't bother with the number of lanes. Like we need to know the number of lanes, but we don't call it multi-lane because they are by default multi-lane. There's no 2-lane freeway. Okay, so these things are fixed for freeways. The analysis procedure, as I mentioned, it will follow the same steps. And the first thing you need is a free flow speed for both cases, for freeways, basic freeways, and multi-lane highways. And I mentioned practical capacity. Okay, the point up to which the speed does not drop. Okay, the flow value up to which the speed does not drop. So that value is 1000 for both these. Okay, 1000 vehicles per hour per lane. Okay, for both cases we have base conditions, meaning ideal conditions, which include there are no heavy vehicles in the traffic stream. These are ideal conditions. Obviously we don't expect this to happen in the peak hour, but ideally our analysis are based on that we don't have any heavy vehicles in traffic and all the drivers are familiar drivers. They are regular drivers. Okay, so they are familiar with the lanes and the speed limit and the directions and everything. Okay, so in these two base conditions give us a maximum flow. Okay, no heavy vehicles means the slow vehicles, the trucks and buses are out. So that means now the cars will give you more flow because they travel faster. And same thing with the regular drivers, familiar drivers. They know the highway, so they are supposed to be faster than the other drivers. Okay, now more explanation about the level of service, each one now. So A means free flow, and you are not influenced by the other drivers. Your speed is as per your choice according to the road conditions. If you want to change your lanes, it's very easy. You have lots of spacing available. If there is a small blockage in one of the lanes, the flow will not stop because you have so much space available in the other lanes. The average spacing between the vehicles in this condition is 480 feet, which is around 24 cars. equal to the length of 24 cars. Level of service B is still considered free flow, but you start to realize that there are other drivers around you, so you start to be more careful, more cautious. Okay, you still have lots of spaces to do the maneuvering and lane changes, but you have to do it with more care now. Okay, still you have gaps available to take care of any disruption, any blockage. You can move to the other lanes easily, but as I said, with more caution. The way spacing now you can see it's less. Level of service C, still you are going at high speed, but your maneuverability is restricted because of other vehicles. So in your lane you can go at high speed, but when you want to change your lane, you may have to wait for the other drivers to give you the chance to do this. Okay, like you want to change your lane, most of the times you will not find the space. You may have to slow down or move fast to find your space in the other lane. So that means that now you have to be more vigilant, because now there may be driver every time or all the way around you on both sides. And in this case, if you have major disruption, then can cause a breakdown, because people need a space or they need time to move in the other lane. So if their lane is blocked, they start to form a queue because they cannot immediately go in the other lane, and spacing obviously is less. Then level of service D is where you will definitely see a decline in the speed. Okay, so even if you are going in your own lane, you don't have enough spacing to choose your own speed. So you have to be more vigilant, and you have to now decrease your speed. When the speed decreases and the spacing is increasing, that means the density is now increasing rapidly. In this case, you are now very close to the breakdown condition. You are very close to the breakdown. This is not breakdown, but now you are getting very close to the breakdown condition. Obviously, maneuverability is very difficult now. The spacing has become even lower than the last case. And now even a minor disruption has a big potential of causing a major breakdown in traffic. Okay, like more potential than the level of service C. Okay, so spacing is now even getting lower. Then we have capacity conditions, level of service E. Capacity means the highway is completely filled, so the only gaps available are those which our drivers are maintaining between their vehicle and the next one. Okay, so they are at minimum gap situation now, minimum spacing situation now. So, and they are moving as well, to keep in mind. So don't be deceived by the spacing of 117 feet between two moving cars. This is not enough gap for anyone to use it for crossing or entering or something like this. Okay, so in this case your maneuverability is difficult. You have to take more care. You will not find gaps, okay, when you want to change the lane. So you have to cause a disruption even to change a lane. You have other drivers have to give you the gap. There is no chance for you now. Okay, so even regular operations, regular maneuvers like changing the lane will result or can result in problems with the queue. Okay, they can cause a queue. Okay, this is called the speed flow curve, which we use for freeways as well as multi-lane highways. So it starts from the free flow speed, then goes up to a point which we called earlier as practical capacity. In the graph they call it the break point. You can see up to the break point the speed does not change, but the flow is increasing. Okay, so drivers don't feel the need to change their speed up to this point. So they are still in free flow up to this point. So after break point the curve starts to decrease and decreases rapidly, you can see, and it goes up to capacity, because after capacity there is no flow. After capacity you are going in level of service F. So this graph only deals with up to capacity. After capacity the graph does not look like this. It cannot continue like this. Okay, so in this region we know the speed of the car is equal to free flow speed. In this region, when you are after the break point, when your flow rate is more than the break point, up to capacity, like I said, after capacity this is not our curve. It's something else which we don't have here. So if you are between these 2 points, okay, then speed will be calculated using this equation. In this equation we are using free flow speed, capacity of the road, and density at capacity. According to the manual, this value DC is fixed as 45, okay, and breakpoint is a maximum flow rate up to which the speed does not change. Okay, so you can see here free flow speed. How do we get the parameters of the curve? We have free flow speed. You can measure it using a spot speed, or you can use an equation. I will show you the equation later on. Then free flow speed must be multiplied with adjustment factors if it is a freeway. For multi-lane highways, whatever you measured or whatever you calculated will remain as it is. Speed adjustment factors, how do we get it? We will talk about it later, but it's only for the freeways, not for multi-lane highways. How do we calculate the capacity? These are the equations for freeways and multi-lane highways. The value from the equation must not exceed these limits. Okay, so you use this equation, you found capacity 2500, you cannot use it because more than the limit, you will use 2400. If it's a freeway, the speed should be in this range. This is a sensible speed limit. If it's a multi-lane highway, the speed should be in this range. For freeways, the capacity should be multiplied with the adjustment factors. For multi-lane highways, no need. How to calculate the adjustment factors? We'll talk about it later. Breakpoint for freeways comes from this equation. So free flow speed and capacity adjustment factors. For multi-lane highways, breakpoint is 1400. So I'm talking about this point. This point. Okay, the starting of the drop in the curve. And then if you go back to this equation, the speed equation for the curve, this part, you see a value of A. So this A value is given here, okay, for freeways and multi-lane highways. Okay, now for different free flow speeds, they have plotted the curves already for our convenience and as an example to understand. Now you can use these curves if your free flow speed is one of them. And these curves are for freeways, so you can use them for freeways. Okay, so if you have a free flow speed of one of these values and the curves, then you can use these curves. Okay, so from these curves, obviously you can see the end of the curve, find out the capacity, you can see the drop in the curve and find out the breakpoint. Okay, but the most importantly, you can find out the level of service. So you look for your flow value here and you go up to the curve of your free flow speed and you can find out the level of service. For example, if my flow is 1000 and my free flow speed is 65, so I come here 1000, go up to 65. Okay, this is my curve and I'm in the region of level of service B. Okay, so this becomes my level of service. Now how did I manage to plot these lines? And you have to do them later on for your term projects and for the example. So every level of service has a density. I told you we call it service measure, the value which gives you the level of service. So level of service A has a density of equal or less than 11 passenger cars per mile per lane. So density is flow upon speed. Density is flow upon speed. Okay, if you take the inverse, so 11 is flow upon speed. 11 is density and density equals flow upon speed. So if you take the inverse of this value, this becomes a slope of this graph, a value of a slope for this graph. Okay, so because inverse of this will be speed upon flow. So 11 is density, density equals flow upon speed. And inverse of that will be speed upon flow, which will become the slope. So if you take the inverse of this 11, this is the tangent theta of this line, the dotted line of level of service A. Okay, similarly 18 is the density for level of service B. If you take the inverse of 18, it will give you the tangent theta for this line. Okay, so you have the density values for each level of service. You take the inverse, it becomes a slope, tangent theta. For that tangent theta, you draw a line in this graph. Wherever the line intersects a curve, that is your level of the line up to which you have that level of service. Okay, so this is how we plotted these lines. So they did it for few values for freeways and few other values for multi-lane highways. Okay, the procedure is the same. Okay, these are the density values, okay, which I was talking about. So A, you can see up to 11, B is up to 18. So you will take the inverse of these values, okay, for the tangent theta of the lines. This is another way of calculating level of service. They use it in the ministry as well. Okay, so what they do is, instead of saying using density, they are using volume upon capacity. Okay, so find out the capacity, find out the volume. Volume, what you have, and capacity, I already showed you the equations. So you can take the ratio, and the ratio will give you the level of service. So this level of service A is up to volume capacity ratio of 0.3. Okay, more than 0.3 up to 0.5 it's B, and so on and so forth. Okay, for every level of service, we said there's a maximum flow rate. We called it service flow rate. So from after plotting these lines, okay, the level of service lines, I can find out the maximum service flow rate as well, because these lines are intersecting the curve, right? The point where the line intersects the curve, that becomes the service flow rate for that level of service. Okay, let me make it bigger. So for example, I plotted a line for level of service A, this line, by taking the inverse of density and so on. So this line, you can see it intersects the curve of 75 at this point. So after this line, the level of service is B. So this intersection point, when I find out the flow from the x-axis, this intersection point is my service flow rate, or gives you my service flow rate. Okay, I can do the same thing for level of service B as well. I go to the x-axis and find out the flow at which the intersection point is. Okay, so this point you can see 820. So 820 is this point, the intersection of level of service A and the curve of 75. So this point, 820 is this point, and so on and so forth. So these are called the service flow rates. For the curves which I have already plotted, they have given us the service flow rates. Okay, this is for freeways, and this one for multi-lane highways coming from these curves. Okay, but the important point is we cannot use these curves until and unless I have the same type of highway and the same type of speed, the same speed. So you cannot use this curve for a 2-lane highway, okay, or you cannot use this curve for a multi-lane highway which has a speed of 51 or 52. There's no interpolation here. There's no interpolation, there's no average. Okay, so your speed should be 50, 55, 60, 45, the values which are shown in the graph. Then you can use the curve to find out your level of service. You can use the service flow rates and so on and so forth. But all these things are restricted. So this is it, and then we'll continue next time, inshallah.